All right, welcome to this explainer. Today, we're diving into something pretty fascinating. We're looking at that exact moment where perfectly balanced textbook equations slam right into the messy reality of physical electronics. We're going to break down exactly what happens when circuit theory meets reality. We are talking about the loading effect.
You know, back in a classroom, it's so easy to just sketch out a flawless schematic where currents and voltages divide perfectly according to mathematical laws. But what happens when you actually build that circuit and plug a real device into it? Well, suddenly, those perfect numbers shift. The very act of measuring or using the circuit completely changes how it behaves.
Here's our roadmap for today. We're going to start with the ideal circuit illusion and the mechanics of dividers before we hit the real-world problem. Then we'll define the loading effect, break down the math behind it, and finally look at how engineers actually fix it. Let's jump right into part 1, the ideal circuit illusion.
So, to really grasp the loading effect, we first have to talk about this fragile illusion of the ideal circuit. It's this perfect theoretical space where everything works exactly the way you calculated it. In this perfect little world, the tools we use have absolutely zero unintended effects on the circuit itself. Take an ideal meter, right? If you place an ideal ammeter in series to measure current, it theoretically acts like it has an equivalent resistance of exactly 0 ohms. It doesn't block or slow down the flow of electrons at all. And an ideal voltmeter placed in parallel, well, that's assumed to have an equivalent resistance of infinite ohms, meaning absolutely zero current leaks into it. But out here in the real world, materials have physical limits. Those perfect values literally just don't exist.
Moving on to Section 2, Mechanics of Circuit Dividers.
Okay, so to manage voltage and current before we attach a real-world load, we use divider circuits. A current divider splits the input current between parallel branches. But the really interesting part is the why behind this physical behavior. You see, the currents in these branches will always naturally divide in a way that minimizes the total energy expended. Basically, they seek the path of least impedance. Mathematically, this creates an inverse relationship. The higher the resistance in a branch, the smaller the fraction of total current it's going to get.
On the flip side, we have voltage dividers. These are an absolute must when you need to supply a voltage that's different from your main power supply, like, say, scaling down a high voltage so a delicate little microcontroller can safely read it. A voltage divider uses series components to satisfy Kirchhoff's voltage law, or KVL. Since the voltage around a closed loop has to sum up to 0, the voltage drops across the components evenly in a direct relationship with their impedance.
Which brings us to Section 3, the real-world problem. Now here is where we pull the rug right out from under those perfect formulas. There's a great quote from Circuit Digest that hits the nail on the head. Ignoring load current is the most common mistake in voltage divider design. And that really is the inciting incident here. When we attach an actual component, a load, it inevitably draws current. In the real world, your output voltage depends entirely on the resistance of the load it drives. The exact moment that current flows to your load, it fundamentally shatters the perfect open circuit math of your divider.
So let's get into it in Section 4, Defining the Loading Effect.
So what's actually happening under the hood when we attach an external load to our perfectly balanced divider? Well, if you compare the ideal state with the real state, you quickly see that plugging a component in fundamentally changes how the whole circuit operates. Think about it. With no load, you get this pristine open circuit output voltage. But add a load resistor, and suddenly your output voltage diminishes. Why? Because that load is demanding a larger current, which ends up acquiring more total power from the original supply. You're basically bleeding off energy that the divider just wasn't accounting for.
And this all stems from one inescapable ironclad rule of circuit physics. Connecting resistors in parallel makes the equivalent resistance smaller. Period. Always. When you attach a load to a voltage divider, you are placing that load's resistance in parallel with the divider's bottom resistor. You've just created a brand new, easier path for current to flow, which drops the overall equivalent resistance of that entire section. This changes the ratio of the whole circuit, causing your voltage output to sag under the weight of the load. That physical, mathematical consequence, that is exactly what we call the loading effect.
Let's look at the numbers in Section 5, the mathematics of loading.
Now let's explore how this general rule of energy transfer messes with the math of complex electronics, like amplifier gain, for instance. When you're designing an amplifier, the theoretical ideal current gain assumes a perfect short-circuit load. But in reality, an amplifier is terminated by finite non-zero values. The effective gain drops at both the input and the output. These specific resistor ratios that mathematically drag down your performance are known as loading factors. So the final real-world output you actually get is quite literally defined as the loaded gain. It's your ideal math, heavily taxed by physical reality.
But there's good news. Section 6, fixing the loading effect.
Fortunately, we don't just have to sit back and accept this performance loss. Engineers have come up with some highly practical solutions to mitigate this inescapable rule of physics. The simplest rule of thumb, make sure your load impedance is at least 10 times higher than the divider resistor it's connected across. This 10 times rule really minimizes that parallel math distortion we just talked about. You can also select high-value resistors to minimize power loss and reduce current draw. Though, a quick aside, be careful with that because it can make the circuit a bit sensitive to noise. But the absolute most robust fix, adding a buffer circuit like an op-amp right between the divider and the load. This is brilliant because it completely isolates the two, allowing the divider to maintain its voltage while the op-amp handles all the heavy lifting for the load's current demand.
It really is fascinating when you realize this isn't just some abstract theory. So here's a thought to leave you with. How is the loading effect being actively managed by buffer circuits inside the very device you're using to watch this explainer right now? These invisible battles between ideal math and physical loads are happening billions of times a second in your phone, your laptop, everywhere. Without clever engineering to fight off the loading effect, modern electronics simply wouldn't work at all. Thanks for joining me, and remember to keep questioning how the messy, real world shapes the perfect math we rely on.